Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of the lecture entitled Variation of. When last we interacted, I said to you about solving this. I hope you solved it, but if you didn't, now's your chance. So you know what to do. Let's see how you did. Now, the first step that you want to do is divide all the way through by that 2, because you see you have to have a 1 there in the way we developed this formula for variation of parameters. And we can look at y double prime plus 9 y on this side, and that's really d squared plus 3 squared, and that tells me that my complementary solution is a linear combination of cosine 3t and sine 3t. So the y1 and y2 are this. And I did make a big deal that you did want to keep track of which ones was 1 and which one was 2, because that comes back later whenever you're talking about your u primes. The Wronskian of these two functions is given by, so we compute the Wronskian and we get 3. So then the particular solution is a linear combination. Here I guess I'm using the formula that I had. You'll get to the same place. And so what you're doing is you're integrating this, and this one is times minus cosine 3t, and this is times sine 3t. Now when I look at this, integral is going to be sine squared, because the tangent is sine over cosine dt. And here, this is just going to be sine, because the tangent is sine of 3t over cosine of 3t, so the cosines cancel out one with another. So this is a pretty easy integral to do. It's the integral of the sine of 3t dt. This one you need to manipulate just a little bit. What we're going to do with this one is we're going to change sine squared to 1 minus cosine squared. Then we'll divide that into each term, and so we'll be integrating the secant. And then this is going to be minus the cosine of 3t. And the integral of the secant is the natural logarithm of this. And we change variables, so we get this 3. And then we're going to do, minus sine of 3t because of this one. And we have the minus out there. And the integral of this one is minus cosine of 3t. And we simplify this, and we get this expression. So this is what y sub p is. So that means y, your general solution, is the complementary solution plus this particular solution. Neat, huh? All right, here's another problem for you to tackle. Find a general solution to this differential equation. Again, you cannot use annihilators because you don't know how to annihilate this thing. You know what to do. Let's see how you did. All right, so this is d minus 1 whole squared as an operator. And so that means that the solutions are going to be, it is a multiple root, so the complementary solution is going to be c1 e to the t and c2 t e to the t. So these are y1 and y2. So if I take the Wronskian of those, I get e to the 2t. And again, I'm using the formula here. You don't have to. You will get the same answer. The particular solution is going to be yp is going to be a linear combination of these. And this is what we have whenever we use the formula. Now look what happens. E to the t times e to the t is e to the 2t, so those cancel. And so I'm just left with t over t squared plus 1. And over here, e to the t times e to the t is e to the 2t, so that cancels, and I get 1 over t squared plus 1. So these integrals aren't really too bad. This is going to be the natural logarithm. I do have to change variables a little bit, so I get a 2 there. And let's see, and here this is going to be the inverse tangent. So I knew that these were our, this is our complementary solution, and I add it to our particular solution. Now, this method variation of parameters can also be used on non-constant coefficient differential equations, provided we know a fundamental set of solutions for the associated homogeneous differential equation. So here I give you that information. So here I give you a differential equation that has variable coefficients. But I tell you that y1 of t and y2 of t, these are linearly independent and are solutions. And you really should probably check that out, make sure they're solutions, and do a Ron scan. But anyway, given that, you can solve this. So follow your nose. You know what to do. Let's see how you did. Now we always divide through by the t. Okay. So, but I told you these were the solutions. So here we divided through by the t everywhere. But then this is y1, this is y2, so I can compute the Wronskian and get this as minus t times e to the t. So the particular solution is given by, it's a linear combination of the two. Now here I have t over t, so this is just going to be t plus 1 times e to the minus t dt. Now this is going to involve integration by parts. And over here, let's see, I have t over t and e to the t over t. That just becomes minus 1. The minus pops out like that. That's just the integral dt. So this is going to be the expression I get here when I integrate that. And when I do the integration by parts, I will get this. Make sure you check with these things. Now, when I take e to the t times e to the minus, when I take e to the t times minus e to the minus t, I just get a minus 1. And over here, when I multiply this out and I simplify it, I get minus t squared minus 2t minus 2. So the general solution can be written this way. Here is my complementary solution, and here is my particular solution. And I make a note here that it turns out that you have a constant C2 here, and you have another 2 over here. You could combine those two, rename the constants, and simplify your answer to look like this. So variation of parameters has a distinct advantage over things we've done before, because it always yields a particular solution provided the homogeneous equation can be solved. And it's not limited to the f of x that we know how to annihilate. And it's also applicable to variable coefficients. This is a general remark. A lot of times in differential equations you can have a right answer, but it looks different. And that's one of the reasons it takes me a long time to grade something, because I really want to double check and say, oh, does the student have the right answer? In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.